Let's talk about first and second order systems and how they relate to measurements and instrumentation. So the sections in the book that apply to this topic are section 5.12 through 5.17. And with all the videos, take note that this is an introduction to this topic. So likely later in your career, if you are working on first and second order systems within measurements and instrumentation, then you will likely need to dive deeper. Obviously, there are books written on the topic and several things on the internet that you could use as resources. But as an introduction, let's step through this. Okay, first and second order systems. Basically, we can simplify a lot of our models that allow us to put them into, first and second order systems, which allows us to understand the dynamic characteristics of the measurement system, as well as the systems that we're trying to measure. So the measurand, if we're trying to measure pressure and temperature, it is very helpful for us to understand maybe what those different systems look like and how they should behave versus what we're actually seeing in the results that we're measuring. So the basic assumptions for first and second order systems are that we have a restoring force like a spring. We've got something that's damping and it's viscous, so like a dashpot or a shock absorber. And then the system can be approximated in a single degree of freedom system. So in general, a 1 degree freedom system is going to have damping or viscous, restorative, linear, and we're going to be just moving the mass up and down. And so we've got the equation here, the forcing function as a function of time, and then the spring constant times the displacement minus our damping coefficient and the related distance function that we have, and our mass times our gravity, or our mass times our acceleration. And so we can rearrange this in a couple of different ways, but we're going to take a few different approaches to simplifying this model and make it work well enough for the measurements that we're going to be taking. So we're going to assume that its restorative force is linear, damping is viscous, and we can use it as a first order degree of freedom. So if we have no dissipative force and no restorative force on the spring, then what's left? Well, F equals MA, and that's an output is equal to a constant times an input, and it's a true linear response. So an example of this would be potentiometers or voltage dividers, and we have used those in the lab when we were measuring the different angles of the parts. And so that would be a good example of a potentiometer, and that is a zero order system. So they're going to have a response that looks like this. So a first order system is we're assuming that the mass is negligible, and that makes these terms in our F equals MA equation go to 0. And so now if we give it a step input, we can see what happens. And so this equation here can be solved to look at our forcing function at time equals 0 minus our spring constant times the distance divided by the forcing function at time equals 0 minus our k times our s at its 0 point is equal to our e to the value here, which is also e to the 1 over tau, and tau is the time constant, which has units of seconds. And so we could have this system have this equation right here. Okay, a second order system, unlike the first order and second order, has enough mass to affect the behavior. So now we can't ignore the mass. So we have F equals MA. We can't cancel out the M in that equation. And so if we give it a step input with the size of F naught, so we just hit it, then we're going to have an equation that looks like this. And so now we've laid out the three different scenarios, the 0th order, the first order, and second order systems, and what those governing equations look like. So in summary, we've got the a single slide wire, or like a resistor that's sliding across a variable number of coils, or a potentiometer. And then we have the first order system, which can be similar to a temperature sensor, where the sensor is proportional to its temperature. And then a second order system would be like weighing systems like load cells, accelerometers, vibrometers. And so these are going to be some of the equations that we walk through. So you can see some of the things that we were able to cancel out going through those. So first order response. So I've got all the variables lined out here. Hopefully this makes it a little bit easier, and maybe you can pause the video and look through those. And we're trying to solve this equation that we simplified down in a previous slide. So if we're trying to solve this for S, then we get S is equal to S at its steady state or infinity plus the difference between the start point and the steady state point. And then we have our time constant and the actual time over the top. And you can see that this is equation 513-ish because the book uses A instead of not. And so in general, S can represent the magnitude of any first order process at a specific point in time. Second order, again, variables over here. And again, we can't delete those variables out. So now we have an equation that looks like this. And we have the damped natural frequency. So as long as we know the spring constant, gravitational, the mass, the damping coefficient, as long as we know all these variables, we can just plug and chug. And we can come up with the solution of these at a specific point in time, given the amplitude of a constant input force. So first order, an example of that would be the temperature measurement system. So we assume that we have a time constant of 6 seconds used to monitor a step change in temperature. So we take it from, say, a room and throw it into an oven. So 75 degrees to 300 degrees. So now we're asking, at what temperature will this device report after 10 seconds? Well, this seems like a very practical problem now, doesn't it? So all this first order and second order talk that we've had and the equations right here, now we're actually putting some application to it. So we're saying if it takes steady state, if we get to steady state, that's 300 degrees. Our initial input's 75, and our tau, or our time constant, is 6 seconds. So then we can just take this equation, plug and chug, and we can end up with the answer, which is after 10 seconds, it's going to be 257 degrees Fahrenheit. So this is, again, a first order system. Example that we're using is a temperature device going from 75 to 300 degrees with a time constant of 6 seconds. So if we have this temperature probe and it exhibits the behavior of a first order system and we give it 6 seconds, it has a time constant of 6, and then we look at it after 10 seconds, this is what's happening. So that equation that we solved right here, this is the plot that it looks like. And so you can see that it takes a lot longer to get all the way up there to infinity, and so than it would be to make initial progress along this curve. Okay, so a little bit more on this time constant, because we kind of threw this time constant out there of 6 seconds. But if we look at it, there's a little bit more going on. That time constant, we're saying, we're defining it as the process is 63.2% complete. And so you can see this time constant here is 1 minus the 0.368. So we've got e to the 1 up here. And so we're saying 63.2% of the process is going to be complete at that 6 seconds. And so at 2 tau, 86.5, at 3 tau, 95%, and 4 tau, 98, and then 5 tau. So you can see that the industry is going to have a standard, and they're going to say, you know what, we're going to consider it to have made it to the final temperature or the ambient temperature after 5 tau, or 5 times this time constant, because we're going to have 99.3% of the value. So we're going to be way up here on the curve. So we're going to say, as long as it's 5 tau, then we're going to just claim that it's complete. And so that is pretty important for us to understand how they come up with that 5 tau. And so if you're picking out something and you see that it has a specific time constant, you know that time constant is where it's generated from. Okay, what about non-step inputs? What if we're not dropping it from the room into an oven? So we have a forcing frequency, and then we have a response frequency associated with it. And so that forcing, instead of just a constant temperature that we give it or a constant load that we give it, now we're oscillating at this cosine omega t rate. It is more complicated because we've got some calculus, but we can do that. We could work through it. And so if we wanted to figure out what this value was at a specific point in time, we could use it. We could do that. And here's equation 518, so we don't have to run through the calculus of it. But essentially, we've got a constant based on initial conditions. And then we have the time constant, which we've looked at before, which has to do with the damping rate and the spring coefficient, the spring constant. And then we have the phase lag, and that's going to be based off of that forcing frequency, our damping, and our spring. So harmonically forced first order response. So this is again a lot like vibrations. So if you've taken vibrations, you probably understand exactly what's going on. If you haven't taken vibrations, then this might be a little bit complicated and you might feel a little bit lost. It's okay. We're just going to use the application of this, not the derivation of it. So the first term is transient, and it fades in a few time constants, leaving a steady response of this. So what that means is we first start oscillating it at this rate, and then that time constant is going to start fading out, and we're going to end up with something that looks like this. And so for static deflection, our initial force that we applied is a static force. So now we can calculate out the maximum amplitude of the periodic displacement. So here's the amplification ratio. So that is our periodic displacement max. And then our S sub S is the static deflection as if it were a static force. And so you can see that the ratio between those two is going to tell us how much more this thing is moving because we are oscillating it instead of just giving it a single force. So harmonically forced, so that means it's oscillating back and forth. The load is oscillating that we're giving our system. And this is a first order response. So the phase lag ratio of the excitation, or the force that we're oscillating it at, period, is time constant. So you can see we could actually pick off values here to get what those numbers would be to put into that equation. The amplification ratio versus the ratio of excitation, another plot, we can pull off values and use those, and so we could see what's going to happen at a specific point in time. And this response is best when the time constant is small compared to the forcing period. And so again, our tau is much less than our forcing period. Okay, so unlike the first order system, a second order system has enough mass to affect the behavior, so we can't ignore this. We start with an input, we give it an F naught, so we just push it one time, we give it a force. We've got our gravitational constant and our mass here. Which again, we've got all of these variables that we can plug in, but this is kind of important for us to understand. For an underdamped case, this ratio is going to be greater than or equal to this ratio. So this, you see the difference here is we've got our spring. We need to make sure that our spring constant is greater than our damping coefficient divided by 2 and then squared. So for it to be underdamped, this has to be true. Whoops. So our critical damping ratio we have here, we've talked about that in the last video. So you can go back and review that if you'd like. But essentially what we've got here is we have this governing equation, and then we can plug in all these different variables into that governing equation to then find out where is the position of our system or our measurand at a specific point in time. So the form of the solution changes for an overdamped condition. So that is x is greater than 1. And so what we've got here is we've got a little bit different scenario going on here, but our damping ratio, remember, we're trying to shoot for this 0.75 or 0.707 or 60 to 75% is kind of the range that we're shooting for. And that is our ideally damped scenario. That means we're going to hit our steady state number as fast as possible with a little bit of overshoot. And critically damped is no overshoot, but it does take longer for us to eventually get to that number. So harmonically excited, now instead of just giving it a single force, now we are oscillating. And now we've got a second order system as well. So our equation that we have is looking like this. So a few things to note in this one. The transient part of it dies out, and so then we can just write the amplification ratio. So this is what we're looking at for underdamped in this scenario. So these two plots, what they're showing us is the frequency ratio, which is our forcing over our natural frequency versus the amplification ratio. And then this one here is showing the frequency ratio, again, our omega over our omega sub n versus the phase angle in degrees. And so you can see that 0.707 again is what we're shooting for. And this is the input that we gave it, right? And so this is our response to that system. And so 0.707, that is our our ideally damped system is 0.707. Here are a couple of videos. Typically when I show this in class, I'll play these videos and reassure the students to not get too hung up on all of this in here, because we're going to use the application of it instead of deriving this from scratch. So this is a pretty good explanation. It does take a few minutes to go through the video, but it is a pretty good explanation of what happens when you hit a resonant frequency. So now let's talk about phase linearity. We usually use a first or second order system for measurements, and not always are they going to be a pure sine wave. However, we can describe it as an infinite series of sine waves, kind of like what we talked about before, where we have multiple sine waves and we add up all those different sine waves. And we can do the same thing with a second order system that varies linearly with frequency and magnitude ratio as a constant. So we could run through those, and now this is the important piece right here. So if you've been in the fog for just a few minutes, have no fear. This is the application of it. So if our natural frequency is greater than our forcing frequency, this is the response that we're going to get. So this sawtooth is what is really happening in the physical world. And then our response of our system, because our natural frequency is greater than our forcing, we're going to see this response out of our measurement. So you can see that we're going to be off a little bit. And so where is that going to matter the most? That is the question to be asking yourself. If you need to know what these peaks are in just the amplitude, then you're probably going to be okay. But if you need to know how far they have shifted in phase, then you might run into some issues. So you can see that as the natural frequency approaches the forcing frequency, now we start getting something that doesn't represent the sawtooth very well at all. And if the natural frequency is less than the forcing frequency, it's not even close. So what does this suggest about where we want to operate our system, or where we want to tune or design our measurement system? So if we're measuring something that's a first order or a second order system, and we are using a measurement system that is a first or second order system, then we are going to want to make sure that our natural frequency is much higher than our forcing frequency. So if you think about it for just a second, now if you did watch those videos, one of them is the Tacoma Narrows Bridge when it had the oscillation and it failed and broke and fell into the river. Another one was a helicopter that was out of sync and it tore itself apart. I bet you're going to watch those videos now that I said that. At any rate, so if you can get in this natural frequency greater than our forcing frequency, then your response of your measurement system is going to more accurately represent reality. So this is what you should take away from this whole discussion. Try to make your measurement system, especially if it's first or second order, make sure that it is higher on its natural frequency than the forcing frequency. Otherwise, you're going to run into these cases here. So here is the summary of all the information that we went through. I know it's a lot. I've got some some example problems and homework problems for you to work through to get a feel for this. And essentially what you're trying to remember is, number one, it's important to know what our measurement system is going to be behaving like. And number two, how is it you can tune or design your system to the point where you're going to get the best measurement possible? So work through some of these problems. Hopefully that will clarify things a little bit more. And we'll see you on the next video.